When we talk about time series, typically we are talking about some underlying processes that we think are relevant. And there are two that are somewhat important to know about and to understand how this affects the modeling decisions we make, and a little bit how we can assess which one is appropriate. So to think about those two processes, you can think about whether the autocorrelation is primarily in the residuals or in the dependent variable itself. And the main thing is, so residuals we often think of as random shocks. Certainly in a time series, the phrase shocks is helpful to understand what we think of as errors. So we can assume that there is some structural relationship between the x variables and the y variables, but that sometimes over time there are random events happening, there are shocks that suddenly make the y value high or low in a particular time period, and that then dissipates again in the next time period. Or we can think of a political variable where maybe we measure support for a particular politician, and we have things like economic circumstances and some attitudinal variables in the population, levels of conservatism, say. And we use those to explain the popularity of a particular politician. And we do this over time, and we think there is a stable relationship, more or less, between these variables and popularity. But then some scandal happens, and in a particular moment, suddenly this politician is very popular or very unpopular. And so that would be a shock to the system. When we talk about a moving average process, we are arguing that when there is such a shock, this shock will have some repercussions for the next one or two iterations. So there's 1 month, say, that a scandal happens and a particular politician is very unpopular, and we expect that impact to be still there the next month, but then maybe in subsequent months this disappears, while the normal structural parameters, how is the economy doing, what are the norms in the population, etc., then become the main explanations of popularity again. So it was a temporal effect that there was this unusual situation that is not explained by the model, that's not included in the model, that led to a deviation. And the argument with the moving average process is that that deviation does not immediately disappear after one time period, but maybe after 2 or 3 time periods. And we can then say that if we model this, we can say that the real error term that we have in our model is a weighted average between the shock in the previous time period and the shock in the current time period. So we have some events that are random, that are not explained in the model, that make the dependent variable differ from where you would normally expect it. And we think that the deviation is some weighted average where the current shock plus a little bit less impact of the previous shock and maybe even less impact of the previous shock. So a moving average means shocks happen, they move y away from where we structurally expect it relative to x. So the mu here in this equation refers to x times beta, is where we structurally think y to be. Then there's some shock, and a moving average process means we are saying we don't think shocks will immediately disappear, but in an MA1 process we say they will disappear after one more time period. So we call this moving average process an MA1 process when the error term is a weighted average between the current shock and the previous shock. We can also talk of an MA2 process. Then the error term is the weighted average between the current shock, the previous shock, and the shock before that. So if we have monthly data on popularity, we say that shocks to popularity dissipate after 2 more months. That means we can also talk about 3 months, 4 months, 5 months. We can talk about Q months and talk about quite a range of weighted averages. And of course, these parameters phi should decline. The current period should have the full impact. The previous period should have a bit less impact. The period before that, a little bit less impact. The period before that, a little bit less impact, and so forth. You would not expect a shock 4 months back to have a bigger impact than a shock 1 month back. So in that idea, we then have a different parameter, a different weight for each of those time periods. A weight for 1 month back, a weight for 2 months back, etc. Now in theory, we can talk about infinite long impacts. We can assume that a shock always has an impact on all future time periods, but that this is gradually declining. And so maybe rather than an individual parameter for each weight, we can put a function on it, like a declining curve. a curve that goes a bit like this. And we can say that one time period back has a very big impact, and then maybe the time period before that 10% less impact, and the time period before that 10% less than that, and the time period before that 10% less than that, and so forth. So then you get a weight of 1 on the current time period, 0.9 on the previous time period, 0.81 on the previous time period, and so forth. Every time 10% less. And that infinitely many, so if you go 1,000 time periods back, there's still an impact, it's just minuscule. Now, it turns out that we can show that if you have these shocks have an infinitely long but exponentially declining impact, that becomes the equivalent of saying that the dependent variable time y is a weighted function of the previous value of time of the value y plus some shock. So that is rephrased here. And that is called an autoregressive process. So where a moving average process means that the shocks are a weighted average between the current shock and a set of previous shocks. An autoregressive process means that the current value of y is a function of the previous value of y. So that is why then the infinite impact comes in, because if there is a shock, and that shock means that the y has changed in the next iteration, then that will also impact the y in the subsequent iteration, etc. So in an autoregressive process, a shock will have an infinitely long impact. And just like we can talk about an MA1 process, we can talk about an AR1 process, where the current value of y depends on the previous value of y. But we can also talk about an AR2 process, where the current value of y depends on the previous value of y and the value before that. We can talk about an ARP process, where y is a function of all p previous legs. And as it happens, if you go infinitely many legs back, if you say that y depends on the previous value and a little bit less on the value before that and a little bit less on the value before that, and that infinitely long, we happen to have an MA1 process again. Now, to determine whether a function is an MA or an AR process is not so easy. One thing you can do is just plot the residuals over time, or plot the data over time. Here you see a simulated value of y over time. For a moving average in MA1 process, the residuals at time t are dependent on the residuals of time, are a weighted average of times t and t minus 1, with no impact before that. And phi is 0.5, so the residuals at this time point are based on the error at this time and half of the error in the previous time. And this leads to a relatively random process over time. So this line goes up and down as if they are just purely random draws from a normal distribution. But you see a slight level of what you could call stickiness. So if there is a high shock, the next iteration probably is still a bit high, but then it goes down again. If there's a mediocre shock, the next one is a bit mediocre again, and then it goes up or down again. So you see a slight tendency to stay where it is for one more iteration, and then it just goes all over the place. We can call this stickiness, whether when we go high we stay high a bit, or go low we stay low a bit, or whether we just go all over the place. So this looks relatively random, but there's a little bit of a tendency to stay at the same place. Here's a similar graph, but now phi is 0.9. So in the weighted average, in the residuals, the previous time period counts much more heavily than on the previous slide. And we see that the randomness reduces and the stickiness increases. There's a greater tendency to stay more or less in the same area from one time period to the next, but if you look a few time periods later, then it's a purely random location again. Yeah, so we have a certain level of stickiness, and here that is greater, suggesting that it might still an MA process, but with a higher level of autocorrelation. Here we have an AR process, an AR1 process with an alpha value of 0.5. So y is a function of half of yt minus 1 plus some error. And we see that it actually does not look radically different from the previous slide. There's somewhat greater stickiness, and what you primarily notice is that unlike the previous graph, which stayed more or less around the same average, so if you look 2 graphs back, it stayed around the same average but just goes up and down a bit with some stickiness. With an AR1 process there is less tendency to stay around a similar mean. And it goes more, it can stay really, if it goes widely up then it really stays up for a while, and it goes down, it stays a good while down. But in that region it then fairly randomly varies. Because the autocorrelation is not that high. So there's less local stickiness, but there is more, in the bigger picture there's greater stickiness. If it goes way up it can stay really quite a while up. And we see that very strongly when we go to an alpha value of 0.9. Now it really stays around in a particular region for quite a while. There's some random variation, But you can see, for example, that after time period 65 or so, it suddenly goes radically down, and then it really stays down for a good while. Yeah, or when around 50 it went up, it stayed up for a good while. This really suggests that it's a sort of a random walk up and down. It's not going around a similar long-term mean with either greater or lesser stickiness, but it really seems to have no long-term mean. It just goes up and down. And just for completeness sake, we have AR processes, we have MA processes. There's no reason that not both can happen at the same time. So Y can depend on YT minus 1, and at the same time, the shock might be a weighted average between the current and the previous shock. We call that an ARMA process. One visualization or one measure that we can have to assess what kind of process we're looking at is the autocorrelation function, or ACF. The autocorrelation function shows you the correlation between Y and previous values of Y, and what varies on the x-axis is K, the size of the lag. So the first bar on this chart is the correlation between Y at time t and Y at time t minus 1. And the second bar is the correlation between Y at time t and YT minus 2. So we can see how much does Y depend on previous observations, correlate with previous observations of Y. And we can work out for the moving average model and the autoregressive model what correlations we expect in an ideal MA1 process or an ideal IR1 process. What does it look like? But more importantly, it helps to make a graph, and this you can also do with empirical data. We can, for example, here we see an ACF of an AR1 process with alpha being 0.5. And with theoretical, I mean this is generated data, it's not real data. But if alpha is 0.5, the correlation between Y at time t and t minus 1 would be 0.5. And the correlation between Y at time t and Y at time t minus 2 would be 0.25. Yeah, half of half. And between Y at time t and time t minus 3 would be 0.125, and so forth. And so this is a declining curve. Yeah, if you see this kind of shape, when you look at the autocorrelation function, then we suspect there's an AR1 process. And if the alpha value is much higher, then this decline is much slower. We see the same kind of curve, but we go from 0.9 to 0.81 to 0.72 and so forth. So we see a much slower decline. This contrasts with an MA process where, because it's only a weighted average of the current residual and the previous one, the current shock and the previous shock, this really dissipates. Like this shock will have an impact in the next iteration, but not 2 iterations later. So for an MA1 process, you get this immediate correlation between Y at time t and YT minus 1. But there's no reason to assume a correlation between Y at time t and t minus 2. So you see this spike early on, and then it just flatlines. And that suggests there's an MA1 process. And if phi is higher, the bar will be higher in the first instance, but the principle is the same. One high bar, and then it stays low and flat. Now in the ACF, we look at the correlation between Y at time t and Y at time t minus k. And then we look at different values of k. One might also want to look at what is called the partial autocorrelation function. And here we also look at the correlation between Y at time t and Y at time t minus k, but we control for the intermediate values. So if we look at the correlation between Y at time t and Y at time t minus 3, we control for Y at time t minus 1 and Y at time t minus 2. And if you look at both the ACF and the PACF, the combination, you can generally get a bit of a sense whether you have an MA or an AR process. So an AR process has a gradually decreasing, exponentially decreasing ACF, as we saw, but in the partially ACF it should have a quick decline, just like we saw with the MA process in the ACF. The Y at time t is correlated with Y at time t minus 1, a little bit less with t minus 2 and a little bit less with t minus 3. But controlling for the intermediate values, it should have no autocorrelation between after t minus 1 for an AR1 process, or after p for an ARP process. Yeah, because the autocorrelation is through the previous value, so if you control for these previous values, that autocorrelation disappears. On the other hand, the MA process has this cutoff right in the ACF. So if you see a gradual decline in autocorrelation in the ACF function, but an immediate decline in the PACF function, it's probably an AR process. If you see an immediate decline in the ACF function, it's probably an MA process. Unfortunately, in real data, when you make these plots, they tend to be much more all over the place, and it becomes a kind of assessment what it roughly looks like.